What's up, everyone? It's Calc time with Miss Wesley. Happy to be here looking at integration by parts packet page 4, and we're going to start with 6 and 7 on this page. Had a question for you. Who took the frog's car? No one. It was Toad. Looking at number 6, I wonder how much this problem surprises you. It surprises me that I've never asked you to take the integral of the natural log of x. You may think I have, but I haven't. We know the derivative of ln. Ln's derivative is going to be a 1 over x. We've actually never integrated it with a basic rule. So integration by parts, surprisingly enough, is going to come to the rescue here. So I want to try this one with you. Now, we've been looking at this method for the past couple of days, and I know my goal is to use a couple variables, sub in to get this to be in the form integral of u dv. And what integration by parts tells me is I'm supposed to get that to equal uv minus the integral of v du. So we've got a little substituting to do. And it looks like I don't have that much to work with. Usually it's like number 7. I've got this one part, the x squared. I've got this other part, the sine of x. A lot of times these start with products or quotients. But this one doesn't. It's just the natural log. So what are our choices here? Let me set up some space for setting something equal to u and something equal to dv. Okay, so I'm supposed to choose u so that it's something where its integral is simpler than its derivative, is simpler than itself. So I'm going to pick u to be ln of x. If it's not, maybe ln of x goes here, but at least it's just a 50-50 chance. And if I do this, let me circle that for starters, what's left over to be dv? This is really weird. Usually I have something else left over. I don't. I've already used ln of x. All I have left is the dx. So it's almost like you're just calling it 1 dv equals 1 dx, and you've scooped up every part of that original. Does this derivative get simpler than itself? It needs to. Du dx equals 1 over x. And we can cross multiply. X du equals dx. We've seen this before. And generally in integration by parts, I need something for this du. So I want to get du by itself here. And it equals dx over x. Keep that in mind. I don't have much here. This is the step where I integrate both sides. So the integral of really just 1 dv, there's a silent 1 there, has to equal the integral of 1 dx. And on both sides, man, integral of 1 is just the variable v. Integral of 1 here with respect to x is just the variable x. And this part of the side work, I just get v equals x. Okay, I guess it's time to plug in, put in the pieces of the puzzle. So first uv, so u is ln of x, v is just x, so times x, minus the integral of v, so x, du, I'll put dx over x. I'll use that substitution there as well. So more things canceling here. The x's cancel in that last little portion, leaving you with just taking the integral of 1 again. Let me write this as x ln x, so there's no confusion, minus the integral of 1 dx. So x ln x minus, I guess this is just x, the integral of 1. So minus x and then a plus c. So I don't know about you, but I think that's pretty cool. We've never taken the antiderivative of the natural log of x, and now integration by parts has let us do that. I probably wouldn't have expected it to be such a drawn-out expression here, but we got what we got. And if you were to take a derivative to try and check this, you would get ln of x back. All right, 7's the next one we're going to look at, and this is probably, I'd say, the most thought-provoking one that we've looked at yet, so I'm going to give this one a star for sure. It looks okay. Okay, so for starters, you see a product here, x squared times sine of x, and use substitution or anything basic isn't going to help with this. So I'm going to try to set up an integration by parts situation where we need to find expressions for u and for dv. We've got to be smart about this. Okay, so u needs to be something where its derivative becomes simpler than itself. I'm going to go for x squared. I feel like its derivative gets simpler than itself. It just is a 2x, which is 1 degree lower. Sine's derivative, right, is going to be cosine. And cosine, I wouldn't say is simpler than sine. It's just a different trig function. So for starters, on my guess, I'm going to slide the sine with the dv. And I know the rule, just like with the last one, that the dx has to go with whatever you call dv. So let's see if we can do this side work here. We need to take a derivative of x squared, so du dx equals 2x, right? Cross multiply, so 2x dx. And solve for du. I think that's all set. I might just circle these so I have them to use for the plug-in a second. Side work with the dv, right? This becomes integral of both sides. For this one, I'm just going to slide an integral sign on the left and on the right. Integral of 1 dv, we can just call that v. Integral of sine of x, right? Antiderivative of sine is going to be negative cosine of x, technically plus c, but we'll handle that at the end of the problem. All right, so far so good. I like the setup. Let's see how far this gets us. This original is now written in the form u dv because we've used all the parts of it, right, to get this expression. Integration by parts formula, so equals uv minus integral of v du. And now for the plug-in. All right, uv comes first. U is x squared. V for starters is negative cosine of x minus integral of v du. So integral of v is negative cosine of x, but watch this. Du has a 2x dx with it, 2x dx. So this is kind of different from the other ones, the other examples that we've seen. While the first part of this is good to go, negative x squared cosine of x, nothing really needs to be done to that. This part's going to take some work. Minus a negative gives you a plus, right? And it's plus the integral of, we'll say 2x cosine of x dx. And what I see here, and don't get too scared here, I just want you to know that this happens from time to time, is we have the necessity for a repeated use of integration by parts. Luckily, I have a lot of space here. We used integration by parts once. It kind of helped us halfway through the problem. Now we're going to use, I'll just write this here, use integration by parts again. This is great practice for us. We're going to try to repeat the process, see if we can do it one more time to get this thing to simplify into something that we will be able to integrate. So I'll switch colors to blue, and now my side work becomes focused on this part. This part's good to go. It'll appear in my final answer. What I circled is what we need to focus on. So let's do this one more time. Let's pick a u and a dv. So let's let u equal some part of this where its derivative becomes simpler than itself. So I like the 2x if we follow the pattern we've been using all along. And dv can equal the cosine of x dx. Okay, so it's like we're doing the whole thing again. Take a derivative here for the side work. Du dx, I like that, just equals 2. Du equals 2 dx. I'll circle it so we don't lose it. And then on the other side, we need to take a integral of both sides. So this side work becomes the integral of what we just wrote. So integral of 1 dv becomes v. Integral of cosine of x, right, is sine of x. And I will circle that. Okay, and now let's plug into this. I'm just going to keep my work just sliding down the page like this. So I want to leave, let's see, well, for now we're just focused on what's circled. So let's get this straight. We want this to become uv minus, I'm just using the integration by parts formula here, minus the integral of v du. Okay, so what is uv? 2x times v sine of x minus the integral of sine of x du becomes 2 dx. Not problematic, nothing we need another integration by parts for because this is just a 2, not a 2x there, just a constant. So we leave the 2x sine of x and we integrate, right? We're going to integrate minus, I'll just leave the constant 2 in the solution. The integral of sine, a function that has a derivative of sine, is going to be negative cosine of x. And now's a time where I might want to not forget about the plus c that'll go on the end. So both of these parts, the 2x sine of x, let's make minus a negative, a plus 2 cosine of x, and the c all need to be part of the answer. And I don't want to forget this other part of the answer from earlier. So all three parts together here, I'll switch to green, and the plus c. So we've got this part, negative x squared cosine of x. What else do we have? We have the 2x sine of x that's here, so plus 2x sine of x. What else? Plus 2 cosine of x. And we won't forget the plus c. Definitely the craziest integral we've taken to date because it involved integration by parts not once but twice, but still really good practice for us. I was thinking it would be a great idea to look at one or two more, so could you flip a few pages ahead in the packet? The one I wanted to look at was number 9 at the top of page 7 here. I want to integrate xe to the x over 2 dx. I think what we just did was tougher than this, so this one I think you could piece through a little bit on your own if you needed to, but let's pick a u value if we think integration by parts is going to be a good idea for this one. Well, u is a part of this function where its derivative is simpler than itself. So I kind of like x for the u choice. That's a very common u choice in integration by parts because its derivative is just 1, right? So du actually equals dx. That's a good thing to know. In the next part for the dv, I like the e to the x over 2, and I know that I have to include the dx as well. I just don't think this part would have fit really good as the u choice because its derivative isn't simpler than itself. Its derivative and its integral, in a way, are itself. But let's work on the integral right now together. For this side work, we've got to integrate both sides. We've got to be careful with this one. So integral of 1 dv is always just v. For this part, there's a rule we can use that we've spoken about before, or we can kind of make a guess at this one. We can say, well, e to the x is its own integral. So I'm going to guess that the integral of e to the x over 2 is probably some sort of e to the x over 2. My guess is to write itself. Well, if I check this by taking a derivative and seeing if I get that back, I don't quite get that back. If I take the derivative of this, I get e to the x over 2, but chain rule gives me times a half, and that 1/2 is a problem. I need to refine my guess and put something here that'll cancel when multiplied with the 1/2 to make this leading coefficient just a 1 like it is here. So I'm going to divide by a half. I'm going to say the integral of this, right, is going to have 1/2's reciprocal in front of it, the 2. Now these 3 parts are set up. We can plug into that same exact formula we've been using all along. Integral of u dv equals uv minus integral of v du. So I think the side work in this one was most of what we really needed to focus on. I'm hoping the rest of the problem is just going to slide kind of easy. uv is going to be u is x. V is what? 2e to the x over 2. Minus integral of v again, so 2e to the x over 2, and in for du, we can write dx. Okay, so this part's fine. I'll just make it 2x e to the x over 2, minus, here's the 2, right? I'll leave the constant. I have to integrate e to the x over 2, which actually we did over here. It is going to be itself. But because the x has the coefficient 1/2, I'll also counteract that by dividing by 1/2 or multiplying by 2. And then we just won't forget the plus c at the end. So check this one by deriving, but it's going to look something like this. Sorry for the handwriting as always. 2x e to the x over 2 minus 4 e to the x over 2. Plus c. One more for the road. Flip to the last page. I love the 2 at the top of page 8, 13 and 14, but spoiler, 13 doesn't actually require integration by parts. You could actually do 13 with u sub. So let's try just starting 14 together. I've got 2 parts to this, and I like that it starts off a fraction. We can handle that. Let u equal something, let dv equal something else. So what are you going to pick for u? What part of this really has a derivative that makes it simpler than itself? They kind of both do in a way, but it's always easier if you see ln in the original function, call it u, make its derivative something simpler than itself, that 1 over x du equals dx. And then that way, for the other part, you can save just x to a power that's always easy to integrate. So this becomes du equals dx over x. We'll leave that there. Then, as you keep going for the next part, the dv, just be careful. You have a 1 over x cubed. That's what I'm going to call it. 1 over x cubed, and the dx that needs to go with it. That's a good choice for dv. Then when you integrate both sides, you're really integrating x to the negative 3 with respect to x. So for your side work, you get v equals, let's go 1 power higher, 1 over negative 2, x to the negative 2. All right, and that's as far as I'm going to take you for this one because I want to see if you can finish it on your own. You want to plug back into the integration by parts formula as always, uv minus integral of v du. You've got the puzzle pieces here. uv is going to go in there nicely. Integral of v du, this is the part to focus on. You want to simplify before you integrate. And check this one with my key. I want to hear how it went for you too. Enjoy your day. See you later.